Get us started. I will begin by looking here at the syllabus just to keep you on track. As I mentioned before, the chapter 4 is the grand finale of these first 4 chapters and where you're going to be taking your exam. So I've done a bunch of examples for you on Monday from chapter 4. I'm going to continue today. We did a bunch of projectile examples. We didn't do any involving circular motion. And so let's have a little discussion on circular motion and do some examples from that. But at the end of that, we'll call it quits and let's go into chapter 5. And you'll see we will transition from chapter 4 into chapter 5. We will go from what I would classify as describing motion to explaining the motion. And what I mean by that is, so far we've just said things like the acceleration due to gravity is 9.8 in the downward direction. It's 0 in the horizontal direction. But we didn't say why. And so going to the next level here is going to explain the motion instead of just describe the motion. With that said, though, this weekend your job is to do the homework from chapter 4 and to finish that up and get ready for the test. Okay? And then there's the little rub I want to remind you of. Obviously, we're going to finish chapter 4. Coming up Monday would be a perfect time to have the test, but as you know, it's a holiday, and so we won't be having the test on Monday. Seems like the next Wednesday would be the next thing to do, but again, as I said at the beginning, we're going to push it to the next Monday so we can have a little bit of extra room and we'll have the overflow. So your test is pushed back a little bit because of that, and I think that's fine in terms of getting ready for the first test. My concern, though, is that many of you might do nothing in chapter 5 until after the test. But if you do that, you're well behind because we'll already be going into chapter 6. Is that making sense? And then the next test, task 2, will come up pretty quickly on you. So best bet is to work on chapter 4 this weekend. Next week, be working in chapter 5. Also coming back onto chapter 4. You don't obviously want to forget it. You're going to have the review for your test. Not this weekend, but next weekend. And so I need to talk to Don, but he'll probably schedule a review on that Saturday. So he likes to do it 2 days ahead of time. So on that Saturday, he'll have you probably come here, do a review. And then that way you can get a feel for how much you do or do not know. And if there's things you do not know, that gives you 48 hours to put things together before the test. Okay, and that's why he likes those 2 days, not just 1 day. And so like I said, I don't want to put words in his mouth or change his schedule, but I'm sure Saturday will be it. So if you can work that into your schedule, it would be highly worth it. As for the test itself, it is like the homework. It is just simply 5 questions. There'll be one on the top of each page. It'll say something like the ball is dropped from a very tall building. How fast is it going after, A, how fast is it going after 3 seconds? B, how far did it fall after 3 seconds? And questions along those lines, just like the homework. So there is not any multiple choice. There's no short answer fill-in like we had in 102. It is just simply problem solving. And so 5 problems, starting with the simpler problems and getting to the harder problems there in chapter 4. But hopefully by the time the test comes, none of them will look hard to you. They will just look like, here's the easy stuff from chapter 1, and then over here's the harder stuff from chapter 4. But I know all that, and you can put it all together. All right? Any questions on the test? Since for most of you, or many of you, this is the first test you've taken with me, and all my tests at this level anyways are like that. The 102 is a little different. Obviously we had, for those of you who had it with me, and I think Dr. Kelly did the same, part of it was multiple choice and part of it was problems that you would fill in. But in this case they're all problems. So look how easy it is. It's just fill in. There's no multiple choice you have to worry about. But again, they are multiple steps like the homework. All right, let's talk a little bit about circular motion then. Let's put a final closure here to chapter 4. And I will start with this question. if I take, and maybe I'll move this out of the way until we get to chapter 5 here. Leave a little room for people coming in late. But if I took an object and made it go in a circle, and so I'll pick the center of the circle, or maybe I'll just make another circle, if you will, for the object that is moving. Maybe I'll even make a dotted line here to label this as the radius. I'll put a little arrowhead with a V, say it's moving like this. And so this object going in a counterclockwise fashion goes in a circle. First question, is it accelerating? Okay, I heard a lot of yeses. Good. Why? Right. The definition of acceleration is change in velocity. All right, so what's the definition of velocity? Yeah, it's a vector, right? It has both a number, which we call it speed, and a direction. And so if an object were to change either its speed or its direction, it of course is changing its velocity. So you can change velocity by either changing its speed or its direction, or perhaps both, which we will do both, and that will make it a harder problem than just one or the other changing. And in this case, then, I would say it's changing for sure its direction. I didn't say anything about its speed, but let's keep it simple here. Let's say it has the same speed, so that a moment later it's here. It still has the same radius, it still has the same speed, v, but of course it's in a different direction. So as you said, is it accelerating? Yes. All right, so here's my question for you. It's the two parts of acceleration. What is the magnitude of the acceleration? What is the direction of the acceleration? And really that's what we need to discuss before we get into some examples. So I'll ask it. Anybody know the magnitude of the acceleration? I know we saw it in Physics 102. What is it?
The speed. Just velocity.
So magnitude of the acceleration. If I said A equals, I might even say A in the radial direction. Or I might say A in a centripetal direction. Anybody know that? Did you see it in the reading? Do you remember it for 102? What is it? V squared over R. So let me give you the answer to get you started. At least for those of you who had me for 102, I just threw that out there and said, we will prove it to you. We will wait till we learn a little bit more mathematics, and we will learn that in Physics 121. So here we are, and hopefully I'm going to fulfill my promise of saying, look, let's go through this. We learned back in 102, like I said, just a statement, that the acceleration is v squared over r. We also learned its direction. Do you remember what direction is it? Yeah, inward, towards center. I'll just say inward. Well, I'll do what you said. How about toward the center? Okay. It's why we call it a centripetal acceleration. It is towards the center of the circle. And again, if you guys had me for 102, and I suppose Dr. Kelly the same thing, that if you had an object at the end, and in 102 I usually take a ball on the end of a string and kind of spin it, and then begin just to conceptually ask, which way is the string pulling? Maybe I should have brought it out again here, but you can imagine me spinning this thing, right? And so if the ball comes across here and I'm holding the string, what direction is the string pulling on that ball? Isn't it towards my hand? And so as it goes around, the string is always pulling towards my hand, towards the center of the circle. And so we did that as an experimental proof. Now let's do it as a mathematical proof. And then we'll use that to do about 4 problems here. All right, so again, let me draw the circle, although this time maybe I'll draw just a section of the circle, something like this. Maybe that would put the center right about here. Let me draw a line kind of straight up. And I'm going to draw a moment before it gets to the top and a moment after it gets to the top. You see, right before it gets to the top, I would say it has a velocity vector, something like that. I try to draw tangents. but I didn't want to draw it too close together. But I would say that is the initial velocity, meaning that is the velocity the moment before it got to the top. Then, a moment later, it looks like that, clearly changing its direction. Now again, let's just say it's going the same speed to keep things kind of simple here for the start. Our definition of acceleration vector, and maybe I shouldn't say this is the definition, this is the equation we worked out. The definition was the change in velocity per time taken, and the instantaneous acceleration was saying what would it be if time were to get shorter and shorter and shorter. So to answer our question mathematically, we're probably better off to do this view as opposed to this view. Let's look at the change in velocity here for a second. Let me draw both of these vectors. If I were to draw the initial velocity vector, it might look something like that. And maybe I'll just put a set of dotted lines. If I were to draw the final velocity vector, wouldn't it look like that? How would I draw the sum of those two? Not that I want the sum of the two, but just to remind us of chapter 3, what would the sum of those two look like? Wouldn't that be the sum? You take the first and add it to the second, right? Arrowhead to arrowhead. Or you could do it down here. Remember that parallelogram? And isn't this down the diagonal the sum of the two? That's not the one I'm interested. Where is the change in velocity vector? The change in velocity is final minus initial. So how do we draw the change? Isn't it the other diagonal, right? And so if I were to draw that one there, that pointing straight down is the change in the velocity vector. And in fact, I think that answers my first question here. One question being what direction is it? The other question being what is the magnitude? What is the direction of that vector? Isn't it straight down towards the center? And I think you can imagine by extension, if I had drawn everything right here a moment before and a moment after, wouldn't I get a triangle that, of course, would be kind of tilted like this, but the change in vector would be pointing towards the center. And so I'll put a little checkbox here. Yep, there's my mathematical proof to correspond with my Physics 102 experimental proof that something that goes in a circle does have an acceleration, and this much of it is telling me the direction of the acceleration. All right, so I guess I've fulfilled half of my promise to you. I've done the direction of the acceleration vector. Now let's do the magnitude of the acceleration vector. And so I'll keep going with this. Although now I will just put the bars around it to say, let me not worry about the direction of the vector. I already got that much figured out. Let's just look at the magnitude. Now that would be the magnitude of the change in velocity vector over the time taken. Okay, so let's come back to this picture. This right here is the magnitude that I would like to know. But let me draw another triangle here that can be very helpful. I'll change colors. I'll come back over to here and draw this one. That would be what I would call the initial position vector. Fair enough? And then if I drew this one, this would be the final position vector. If I drew an arrowhead across the top of them, what would that be? Do you see the same parallelogram here, right? I haven't drawn the complete parallelogram. The complete parallelogram would look like that, right? And along this diagonal would be the sum of those two, which I'm not interested in. What would this diagonal give me? Yeah, so isn't that the change in position? And that kind of makes sense from my picture, right? It went from here to there. There is my change in my position vector. All right, so take a close look at this green triangle for a moment, but then compare it to this triangle that we made with our velocity vector. If I were to kind of label this and say, let's call this little angle here theta. Theta. So maybe the whole thing is 2 theta. But as I look at this little picture, I'm saying that a moment before it gets to the top, there's some angle, albeit a small angle, because I am trying to take the limit as time goes to 0. Actually, I should fit that in there. The limit as time goes to 0. So eventually we would be saying that that angle gets smaller and smaller. But before we take the limit, there's some angle, albeit small, maybe 1 degree. But how does that compare over here to this triangle? Well, again, maybe you'll see it a little bit better right here. If you remember, this right here is representing that vector, right? And so the radius comes out and would touch this perpendicular. And so a line that is level across here is going to have a small angle, right? And that small angle would be, let's see if I can make the triangle here, but this angle here, right, horizontal and in here, wouldn't that be 90 minus theta? And so if that's theta, that's the 90 minus theta. So this little tiny one in there must be theta, which is great because that really is saying that that angle is theta and that angle is theta. What I'm trying to point out then is the triangle that I make with the position vector and the triangles I am making with the velocity vector are actually similar triangles. I'm not saying they're the same size, but they have the same shape to them. This angle here is the same as that angle, and they are each a isosceles triangle. Isn't this, if it's the same speed, that leg equal to that leg? And since it's a circle, isn't that radius equal to that radius? And so that tells me this angle here is the same as that angle there because it's an isosceles. And then, of course, that means that angle is the same as that angle, so that triangle is similar to that triangle. Now I'm going to take advantage of your geometry. With similar triangles, you could take the ratio of any two legs. Wouldn't it be the same ratio of the same identical legs over here? And that's going to be the key step. So I'm going to come over here and say delta V is to V. And I'll just do magnitude. So that length is to that length as that length is to that length. So delta R is to R. Now remember, over here in this equation, what I'm trying to find is I am trying to find the magnitude delta V. Well, there it is. If I move V to the other side of the equation, I then have, for delta V, I have V times delta R over R. If I simplify that compound fraction, I get V over R, delta R over delta T. If I take the limit as time goes to 0, what would you call that? how position changes with time. Isn't that velocity? So that is velocity. So I have v squared over r. There it is. There's the second half of the proof I said I would give you. Okay. And so my point here at the beginning is to realize that part of our two-dimensional motion is going to involve things going in a circle. Like I said, last time we were together, we did a lot of projectile motion. True. But now we're going to look at things moving in a circle. And the key point I'm trying to illustrate by mathematical proof, and then in 102 experimental proof, but here's the key point. Something moving in a circle. Is it accelerating? Yes. What direction is the acceleration? Towards the center of the circle. What is the magnitude of the acceleration? V squared over r. Exactly. And that's what I want to work with. Now, let's add one more step to this. Notice that all of this discussion implied an object moving in a circle at the same speed. So what I've done so far maybe would look something like this in a picture. That, okay, I have a circle. I have, say, the center of the circle. I have, say, the object right here. I will say it's moving with some speed, and let me call it some initial speed. It has a direction, so let me make it a vector. But as it goes in a circle, and if it is only going at a constant speed, wouldn't it have an acceleration vector? And so that acceleration is in the radial direction. It's towards the center of the circle. And so sometimes your author will call it the radial acceleration. Sometimes he will call it the centripetal acceleration. Whatever word you want to use there, the idea here is this, and I'll use radial, is that you would have that much acceleration towards the center of the circle. That's how much you need to make it turn. But that may not be the whole story. What if it's also going faster? So it's not just turning, it's also going faster. Well, hopefully that's straightforward. Haven't we been doing problems where objects go faster? I mean, let's just talk about it. Way back in chapter 2. If I was going this way and I wanted to go faster, what direction would have to be the acceleration? Right? In the direction I'm moving? But what about this way? What if I'm going this way and I want to go faster? What direction is the acceleration? Again, right? Direction you are moving. And so anytime you have a direction, an acceleration in the direction you are moving, that's going to make you go faster, right? How would you go slower? If I was going this way and I wanted to slow down, what would be my acceleration? Opposite of the direction I'm moving, right? Okay, so adding this here, I could say that in addition to having an acceleration that is making the object turn, I could have an acceleration which I will call the tangential acceleration. Tangential being tangential to the circle, right? It's in the direction that the object is moving. Wouldn't an acceleration in this piece make it go faster? And so the total acceleration would be a combination of the radial part, the part that is making it turn, and a tangential part. The tangential part is the part that is going to make it go faster or perhaps slower. In my diagram, I am showing faster. What would my diagram look like to make it go slower? Maybe I'll change colors. Yeah. So the tangential would be opposite to the direction it is moving. That would make it go slower. Now if it's still turning and going slower, it would still have a radial direction. And so in the green would be showing the two components. The total acceleration, you would have to add those two components together, right? Remember all that great math we learned in the last chapter, chapter 3, right? Could you put together two components? An I hat and a J hat? Please say yes. Yes, right? And so, again, this chapter is going to be asking you to put together the ideas that we've learned in the last chapter together with two-dimensional motion. And so, the two things we will be putting together is a component, how much acceleration is needed to make it turn, how much acceleration is needed for it to change its speed. So, the magnitude of the total acceleration, then, would be the radial part and the tangential part. You would combine them together. Now they're at right angles, they're components, so you'd have to use Pythagorean theorem, right? We would say add them in quadrature to get the total result, but that's what we get for things going in a circle. Well, let's try a bunch of examples to see how all this comes into play. And so I have a list here of some examples, and let's go through them. And if time allows, which I hope it does, we will then move into the next big step, which is chapter 5, and we will get to Newton's 3 laws of motion. And it would be nice to kind of review Newton's 3 laws of motion, and that's really kind of what I'm hoping and planning to, is just repeat what you already learned in 102 without the calculus. We'll start the calculus and Newton's laws of motion the next time we get together, Monday's a holiday, next Wednesday. But at least I want to throw that out there and remind you. In fact, maybe this is a good time to remind you. This class can be summarized real simply as taking the basic laws of physics you learned in your previous physics course. I keep saying physics 102, although I know not all of you took 102. Some of you, did high school physics or another community college. But if you took it here, it was physics 102. Take those basic laws of physics. Take all that wonderful math that you've learned, and even some new math with the I hats and the J hats, some math I've given you since you've been here, and we're going to put all those together and allow us to do more complex problems than we've been doing in our previous physics course. Well, let me try number 29. I think 29 is a good place to get started as we look at our two-dimensional motion here in chapter 4 and things going in a circle. And so I've got the book up here, chapter 4, number 29 is right here. I'll move it to the top of the screen. But again, let's read it together. Here we have a train slows down as it rounds a sharp horizontal turn, slowing from 90 kilometers per hour to 50 kilometers per hour in 15 seconds. The radius of this curve is 150 meters. Compute the acceleration at the instant or at the moment that the train reaches the 50 kilometers per hour. Go ahead and assume that it slows down assume it continues to slow down in this time at the same rate. So it has a slowing down rate that's a constant. Okay? Now, with that said, let's see if we can kind of draw a picture. Let's say this is the train. So there's some kind of straightaway for a while, but then it hits a turn. And so it begins to make a turn. And I'm not really sure how far the turn goes. It doesn't really matter. I just know that this turn has some kind of center to it that would make it a distance of 150 meters, I think is what I read there, right? 150 meters. Okay, that being said, it looks like the train at this point, and I'll put a little arrowhead and say it's traveling at 90 kilometers per hour. It slows down, taking 15 seconds to get to, say, this point, where it is now going 50 kilometers per hour. The question is, what is the acceleration when it is at this point? All right, well, let's take what we just talked about. First of all, is the train turning? Clearly, yes. So does it have what I would call a radial acceleration?
Yes.
Yes. So maybe labeling that in green, I would say there must be some value of acceleration, or at least part of the acceleration is pointing towards the center. That would be a component of it. And as we said, that number would have to equal numerically what? V squared over r. But also, what else is happening? It's not just turning, it's also slowing, right? So, in addition to saying part of the acceleration is turning it, the other part of the acceleration is slowing it down. So, how would that fit in this diagram? Opposite of the direction it is moving. And that would mean then the total acceleration is the sum of those two components. And so I'll make a parallelogram out of this. And since they're at right angles, that would be a rectangle. And so the total acceleration is really that. And that's our acceleration vector. That acceleration vector can be viewed as part of it towards the center of the circle and part of it tangential to the circle. The part that's towards the center of the circle is the part that's making it turn. The part that is tangential to the circle is the part that is slowing it down. And so let's calculate each of those. And we can do those separately. For example, the radial part, as we just showed by proof, would be v squared over r. You need to know the speed and you need to know the radius. So that's easy for this problem. You can see why I did this one first. I gave you the speed, I gave you the radius, and now it's just a matter of plug and chug. However, it will take us back to chapter 1. There are some unit conversions here. I'll write it out first by saying, well, the speed is 50 kilometers per hour and the radius is 150 meters. Well, let's go back to chapter 1. Kilometer means 1,000, right? What does an hour mean? Well, so many seconds, right? How many seconds are in an hour? Yeah, 60 times 60, good. 3,600 seconds. So doing a direct substitution for our unit conversion, I'll leave the number 50 alone. But in place of the K, I will put 1,000. And in place of the H for hour, I will substitute 3,600 seconds. And if I got my calculator out, that would give me now the speed in meters per second. And I will do that in just a second, but I'll put the 50 or 150 meters down below. So in the numerator, I would have a 50 times 1,000. I'm just going to enter that as 50,000 into my calculator. And then divided by the 3,600, come up to be 13.8, repeating, meters per second squared, 150 meters. And so squaring that number and dividing it by 150 comes out to be 1.29. And let me just see what the units come out to be. Meters squared divided by meters is a meter per second squared, which is perfect. Isn't that the unit for acceleration? And so it does match. Not a surprise, it should. That's, again, back to our chapter 1. That's our unit analysis. Use your logic. Come up with the formula. Work out the formula. check your units. Your units should come out to equal the units that are used to measure that variable. If they don't, you've clearly done something wrong. And so mine do match. So I'm feeling pretty confident that that's the right equation and the right idea and the right formula. Of course, the other part of this problem is the tangential part. The tangential part is how the speed changes. Well, maybe I'll write it this way. Change in velocity over time taken. And maybe I'll just put a vector with the bars there to say, I'm not talking about the change in the whole vector, which would include a change in direction. This part of it, I am talking about just the change in the speed. How much did its speed change? Now, you may argue that if you do beginning to end over that whole 15 seconds, isn't that really the average acceleration? And I should say tangential acceleration, because it's over the whole 15 seconds, and they want to know it at that instant. But fortunately, they were nice to me here and said something real important here. Go ahead and assume that its slowing rate is the same all the way through. So in other words, whatever I calculate for the average over those 15 seconds is actually the same as the instantaneous, right? That's the only way you would get an average that would be the same as the instantaneous. Maybe a good example is, let's say in a week and a half, everybody takes the test and I go to calculate the average and I realize everybody in class got 95%. Wouldn't that be great that everybody got 95? But it would also make it easy. How am I going to calculate the average? Well, that's a piece of cake, right? I mean, I probably won't even bother to get my calculator out for that one. I can just see it right away, right? So if everybody got the same score, that is what I'd call the instantaneous score of every individual here. So that's what I'm going to do. I'm going to calculate the average tangential acceleration during those 15 seconds. But what I really want to know is the instantaneous, but I can argue that the instantaneous is the same as the average in this case. All right. With that being said then, I can take that final speed, which is 50 kilometers per hour, and subtract the beginning speed, which is 90 kilometers per hour, and divide it by the 15 seconds. Fair enough? I'll even take one more step. I don't know if this makes things clearer. I think it does a little bit. Let me not worry about pluses or minuses for now. Let me just take the absolute value. So instead of me writing a negative 40, which really is implying then that, okay, if this way is positive, my acceleration is opposite of that. No problem. I can see that in my picture. So I'm going to drop off the minus sign unless I need it, but right now I'm just going to do the magnitude, and so I'm going to put here 40 kilometers per hour and divide that by the 15 seconds. And of course now we're kind of back to the same thing we had in this first part. Was let's do our unit conversion. So this is 40 times 1,000, and there's a meter. Do a substitution for an hour. An hour is 3,600 seconds, and then I can divide it by the 15 seconds. And so, like I said, chapter 4 is really going to ask you to do everything you've done in those first 3 chapters. You see the unit conversions right here. You also see the directions. In a minute, you're going to see the components, the chapter 3, because I got to do Pythagorean's theorem to get the total acceleration and the direction here. So in the numerator, I have 40,000 divided by 3,600, which comes out to be 11.1. I'm going to divide that by the 15 seconds, and coming up with 0.741. And if I look here, that's meters per second each second, which when I take that compound fraction and simplify, becomes meters per second squared. And as it should, right? I'm getting an acceleration, so it should come out into those units. Yeah.
What if it asked for the acceleration over the entire period?
Well, there would only be, there's an acceleration at each instant.
But not like an average acceleration.
Well, you could say an average then, sure. I'm not sure that would be useful at all. So I'm not sure they would ever ask it. So I guess I don't want to go too far down the road of how would I calculate an average over a time period. But what does the train do? What does the baseball do? What does the rocket ship do? What does the asteroid do at that instant is based upon what is the acceleration at that instant. So we want to know what is the acceleration at that instant. And so that's why they asked, what's the acceleration at that instant? Although I did use the average tangential to get the instantaneous. But notice I did not use the average radial. That is changing, right? Because here it's going fast. I would have a different radial acceleration here as opposed to here as opposed to here. So and that's why they made it very clear, calculate the acceleration here at that instant. Not the average of it, but at that instant. And that's where I got the 50. Any of the other moments in time, it would be a little bit bigger number and a little bit bigger radial acceleration. All right, so I have the two components. Let's come back to the question. Did they ask for the components or the whole thing here? Now see, they had compute the acceleration. So I think they want the total, what I call polar coordinates in chapter 3. They want to know the magnitude of this. And so, if I may, I would say that number right there, the total acceleration, at least in magnitude, would be the two components. So it would be the 1.29 squared plus the 0.741 squared, and then take the square root. And so the whole magnitude of the acceleration is, of course, what you would feel if you were in the train. It would be also what the traction would need, or the forces of the rails on the train would need in order to turn this thing. 1.29 squared added to 0.741 squared, taking the square root of all of that, is 1.49. So 1.49 meters per second squared would be half the answer. That is the magnitude of it. The other part of this, because they just say acceleration, and acceleration is a vector, so I think we need to also include direction. Direction from what? Kind of our choice. How about I do that? Some angle relative to the radius. All right, so in that case, the tangent of theta is the opposite, so that's the tangential piece, over the radial piece. All right, well, the tangential piece is the 0.741. The radial piece is the 1.29. So if I take the inverse tangent of that, I get 29.9 degrees, pretty close to 30. And so there's our first example of something turning in a circle. It has a radial part, it has a tangential part. Again, radial part making it turn, tangential part making it either speed up or slow down. And then of course we can apply all that wonderful vector stuff we are learning or have already learned as we're working along. Well, let's try 30. 30 is right below it. It's another good one, I think, of something moving in a circle. It's got a lot of little subtleties in it. It really is going to challenge your brain in terms of what do we mean by components and unit vectors, but also what do we mean by going in a circle. And that's why I picked it. I think it's a good one that if you see the pieces in this, you're probably in a good position to do quite well, both on the homework and on the test with the circular motion stuff here. All right, so I'll read it together here. But let's look at this. It says a ball is swinging. All right, so here's our object. It's a ball. It's swinging in a vertical circle at the end of a rope that is 1.5 meters long. In fact, maybe I'll just stop there and say, all right, here they have a vertical circle. There is some radius, 1.5 meters long. And man, maybe that's so obvious it doesn't need to be pointed out, but isn't that what they're really saying? They're giving me the radius here. The rope is 1.5 meters long. The ball is at the end. We're swinging it along. They've told me that radius, and I'm going to need to know that, I'm sure, in order to do some of my calculations. All right? Now it says when the ball is 36.9 degrees past the lowest point and on its way up, its total acceleration vector is, and here they give it me in the I and j hat components. Now they didn't give me a picture to work with, so I'm going to assume that they're talking about the traditional grid where y is positively up and x is positive to the right. I don't think they meant to change that. Here's why, and let me kind of draw the x and y coordinate grid outside of that picture for just a second. Well, what have they given me? Well, again, they've given me the acceleration vector. They've given me the position of the ball at some angle on its way up. Well, let's do this one. What would a negative 22 I hat and a positive 20 j hat look like? So it would go this way, 22, actually it's 22 and change, isn't it? 22 and a half, and it's up 20. 20.2 and change. And so they're really saying this is the acceleration vector. It's not quite 45 degrees, fair enough? But it's kind of close to 45 degrees, right? 45 degrees you would have the same on the x and the same on the y. So this angle here is just shy of 45 degrees. I'm probably even going to need that angle later on here. But what I am trying to say then is it looks like to me in their discussion is the ball is right about here heading up because they say this angle is 36.9 degrees. So it says it's 36.9 degrees past the lowest point on its way up, and at that point has an acceleration vector. So let me put a horizontal line, maybe even use the red here. It has that vector, which by the way means if this is roughly 37, doesn't that make this a 53? And so the acceleration vector looks like that. Maybe I should draw this a little better here. Here's the point. Here's the acceleration vector, A. What is that angle? As I mentioned in this picture, it looks to me like it's a little less than 45 degrees. But let me get it accurately. All right, so I'm going to go inverse tangent of the 20.2 divided by the 22.5. And that's 41.9 degrees. So this angle here is 41.9 degrees. But the 36.9 taken away from 90 degrees, the complement here, so let me go dot, 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 dot. That's the radial vector. That's towards the center of the circle. That angle that big angle right there is 53.1 degrees. Fair enough? All right. So, again, like all these problems, take a little while to kind of digest what they're trying to say in these pictures. And what do all these numbers say to you? And we're back to that same phrase I keep saying. Make sure you read the math. There's a meaning behind these numbers here, and of course that's what they're giving me here. Okay. They've given me the acceleration. And that's what I meant earlier when I said we've got this thing going in a circle, and we also have these component vectors. Now here it says, at that instant, A, sketch a vector diagram showing the components of the acceleration. Well, I suppose that's really what I did right here already. So I guess I've done A. This right here is the x component, and this right here is the y component. And that's the x and y component. But notice that is not the radial and tangential components. That's how we think about a circle. We don't think about a circle in terms of its x and y components. We think about it as how much is radial, because that changes direction, and how much is tangential, that changes its speed. So we're going to have to convert from these Cartesian coordinates to our polar coordinates. That's what I'm trying to emphasize. So I think I've answered A. At least I have if they are asking for what are the components, and by that they mean the x and y components. I have not found the radial and tangential components, but I have found the x and y. In fact, they were just given to me. But watch this. B, determine the magnitude of the radial acceleration. So that's why I'm pretty sure in A, when they said the components, they were not asking about the radial and tangential components, not in polar form, but in Cartesian form. Because B is asking me for the radial one. All right? So maybe switching colors here and coming over to the diagram here, here's really what they're saying. This is that acceleration vector. It has an x and y component that I'm not even showing in this diagram. It's over here in this diagram, sure. But let me keep it off of this diagram, otherwise it'll look too cluttered. But what they're asking for is, could you think of this vector as being made up of so much in the radial direction plus so much in the tangential, right? And so that's really what they're asking. This blue piece right here, how much of this acceleration vector is in the radial direction? Now, keeping that in mind, that is the part that would be making it turn. So I would expect to have a radial, and a pretty big radial one, because isn't it turning? Sure. Looking at this picture, it would tell me, though, that I also have a tangential, which that means it's changing its speed. Looking a little closer at the picture, this would tell me it's tangential, opposite of the direction it's moving. So what would that tell me? It's slowing down. So this ball, as it is swinging up, is not only turning, but it is also slowing. And that doesn't surprise me. If I were to swing a ball on the end of a string as it's going up, I would expect it to turn and to slow on its way up. I don't think they said slow, but I can see that then after I start drawing these vectors and I start reading into what does all this physics mean to me? What do all these numbers mean? All right, so I guess this is the answer to A, and the answer to B would be, let's find the radial component. Well, the radial component would be the magnitude of the acceleration vector multiplied by cosine. And do you see it here in this picture? How do I get the radial component? There's my right triangle. Wouldn't I want cosine of that angle? So I'd want that magnitude of that multiplied by cosine of that, right? This is the chapter 3. What is that angle right in there? Isn't it that minus that? All right, so I want cosine of 53.1 minus 41.9. But how do I get the magnitude of it? Well, don't I have the Cartesian coordinates of it? So wouldn't this be the 22.5 squared plus the 20.2 squared square root? So there's the magnitude of the acceleration vector, which I can get from the Cartesian points. Once I have its magnitude, then I can say how much, and I'll use a math term here, how much of that vector is projected onto the radial vector. And so then I have cosine of 50, well, maybe I should just subtract these. What is 41.9? I'll borrow a 2. So that's a 0.2, that's a 1,1. So it's 11.2 degrees. And so now I can get the radial piece. All right, so 22.5 squared added together to 20.2 squared, taking the square root of all of that, gives me a magnitude of 30.2. And just in case I need it later on, I'm going to put it in this diagram. 30.2 then is the total magnitude of the acceleration vector. Then if I multiply that by the cosine of 11.2 degrees, I will get a number which comes out to be 29.7 meters per second squared of how much is in the radial direction. And so there's B. C goes on to then say, from this, can you determine the speed and the velocity of the ball? Well, that was our whole discussion. We know that the radial part is equal to the speed squared divided by its radius. And so we just got the radial part. We also know the radius. So V equals the square root of the radial part of the acceleration times R. And that's why it was so important for us to figure out what was the radial part. We know that the radial part is connected to the speed. So I'm going to take that 29.7, I'm going to multiply by the radius, which we said at the very beginning was 1.5. I'm then going to take the square root of all of that and get a speed of 6.67 and meters per second. And there's half of the answer to C. That's the speed part of it. They went a little further to say it's velocity, so they want direction in here. And so to finish this, I would say, all right, let's write this in terms of components. Since they gave me x and y components to begin with, perhaps I should give the answer in x and y components. So let's come back to this little diagram here. As we said earlier, this angle up here is 36.9 degrees, which is how we got this angle, because that was the complement. That was the 53.1. But this angle there would be 90 degrees because that's the radius and that's tangential. And so that means this angle would be the complement of that one, which was the complement of that one. So we're back to our 36.9 degrees. So as I look at this picture, I know that it's heading upward at 36.9 degrees. So to get the x component, I would take its magnitude, the 6.67 meters per second, and multiply it by cosine of that 36.9 degrees. That would be how much of the speed is in the x direction. And then the other piece, the 6.67, there's the magnitude. Multiply it then by sine of 36.9. That would be the j hat component. So 6.67 times cosine of 36.9 degrees comes out to be 5.33 meters per second in the x direction. And 6.67 times sine of 36.9 comes out to be 4.00 meters per second in the y direction. And so there's my answer, speed and direction. Fair enough? Looking a little easier? How about a couple more? I said we should do a few, and we've done 2, but how about 2 more? And then we'll move on to start reviewing Newton's laws of motion and what you learned in your 102 here. How about 47? There's another one that has some kind of circular motion in it. Let me clear off the board here. And say, all right, let's look at this. I think this is a pendulum one, if I remember right. All right, so what does it say? 47, a pendulum with a cord of length r equaling 1 meter swings in a vertical plane. All right, well, I'll take that as my starting point here. The pendulum is maybe tied to the ceiling or some kind of support up there. And it has a string, I think it says cord there, that is 1 meter long, which of course means it's going to be swinging back and forth. So it's going to swing, and I think this one has it swinging pretty high. Going all the way up till it's horizontal, I believe. It says when the pendulum is in the 2 horizontal positions, theta equaling 90 degrees and theta equaling 270 degrees. All right, so when it swings this way, when it swings this way, I'll call that then 90 degrees, since we traditionally call counterclockwise a positive angle, although we don't traditionally call straight down 0, but I think that's what he's referring to, because if he says it's horizontal at 90 degrees, he's saying, so straight down is 0 angle. And so he's got it swinging one way, that's 90 degrees. And the other way, I would actually call negative 90 degrees, but he labels it as a positive 270. But the pendulum can be over there. So how you want to label it isn't real important. The idea is that this pendulum is swinging all the way up to the horizontal position. Okay? And so when a pendulum is in the 2 horizontal positions, its speed is 5 meters per second. Okay? They don't really say which way, so I'm not going to draw anything, but it's 5 meters per second. A, find the magnitude of the radial acceleration and the tangential acceleration at these 2 points. B, draw a vector diagram to determine the direction of the total acceleration of these 2 points. And C, calculate the magnitude and the direction of the total acceleration. Well, maybe I'll do B first, because B is the part that I would encourage you to always do, whether they say to do it or not. Draw the pictures, draw the diagrams, get a good physical understanding of what is going on here. So, at the 90 degrees, as opposed to at the 270 degrees, I would draw it coming out and looking something like that, whereas this one, I guess I would draw it going back like that. But what I know is it is moving, and they don't really say up or down, and I suppose that doesn't really matter for what the question they've asked. I do know that it is turning in the radial direction. Why don't I just say it is swinging upward and it is on its way to go even higher? And if that's the case, then the velocity would be going up at 5 meters per second. But there definitely would be a radial part. Now, gravity would also be slowing it down, fair enough? And gravity is pulling with an acceleration straight down. That would be, at this point, a tangential piece. And so they were nice to us to give us right at the magical 90 degrees of horizontal. So I have an acceleration of 9.8 that is opposite to the direction it's moving, so it's slowing down, at least in my picture. Again, they don't say whether the pendulum is on its way up or on its way down at that point. But I'll say it's on its way up. And so that tangential piece is 9.8. The radial piece is actually then pretty easy because it's the v squared over r. And they gave me the v as 5, so I'll square it. They gave me the r as 1, so that makes the 25. And if I put in my units here, this is meters per second squared. So I have the radial and the tangential part. In this one here, nothing's really changed. Gravity is still pulling it down. That would be the tangential piece of 9.8. Then maybe just for the sake of discussion, let's say it's also swinging up just on the other side at that point. And it would have then a radial part. But again, that radial part would be v squared over r. And the v is the 5 meters per second that you are going to square. And the r is the 1 meter. And that's where the 25 comes from. And if you check your units, it's 25 meters per second squared. And so they are essentially the same problem, just one is swinging to the left at an instant, and the other one is swinging to the right. So I think I've answered the B, which is draw the vector diagram to determine the direction of the total acceleration. Well, I guess I'm not quite done. I haven't done total acceleration, so maybe I'll do the total in red. So looking at this, I have one vector that isn't fairly represented in my picture. 25 would be much bigger than the 9.8, so if it'll be okay, I'm going to draw it like that and extend my original drawing way out, because they're saying that's a huge number, 25. I didn't know how big it was going to get till I actually calculated it. But that one should be about 2.5 times that one. That was roughly 10, and that's 25. So that would be the vector diagram. These would be the two components. One of them is 9.8, one of them is 25. Together, that's going to make that vector. Over here, same thing. That I need to realize now, this is huge, 25, compared to this one, roughly 10, 1, 2.5. And so that would be the sum of those two, making a parallelogram. Okay, now I think I finished B. Let me read it again here. B. Draw the vector diagram to determine the direction of the total acceleration. Well, it says to determine the direction, so I guess I'm not done. Let's get that direction. I think they want to know an angle in here. Now, fortunately, it's the same geometry, and so whatever angle I get, say, there from the horizontal would be the same angle I would get there from the horizontal. And so we would get tangent of theta is the opposite, so that's the 9.8, over the adjacent, which is the 25. And so grabbing my calculator, I can go inverse tangent of 9.8 divided by 25, and we're looking at 21.4. So 21.4 degrees would be that angle. All right, now finally I think I did B, right? I've drawn the vector diagram, and from that I have the direction. Let's jump back up to A. A says, find the magnitude of the radial acceleration. Oh, so I guess I did that before I even read it. That's how I got the 25. I took the v squared over r. Okay, so I've done that. And the tangential accelerations. Okay, so I guess I did that. The tangential I got from gravity. So there's the tangential, the 9.8. There's the radial, the v squared over r. So I've also answered A. So I've got A and I've got B. Let's go to C. Calculate then the magnitude and the direction of the total. Well, there's that direction again. I don't know, maybe they are saying it twice, or maybe they didn't really mean for you to calculate it in B, but I've already got the direction. That's that angle theta, the 21.4. The last part of this then is what is the magnitude of the total acceleration. And again, just like we've been doing in chapter 3, it's Pythagorean's theorem here. We need to add up these components. So the horizontal piece is the 25. The vertical piece is the 9.8. Let's add them in quadrature and see what we come up with. And so I have 25 squared, and I'm going to add that to 9.8 squared. I will then take the square root of all of that and get a 26.9. So 26.9 meters per second squared is the total acceleration. Fair enough? You guys are looking like this is way too easy. Either that or you're still asleep, but I'm hoping it's the former, not the latter. You're like, okay, I get the point of all this. I said I would do one more, so let's do one more example. But I'm hoping, are they all beginning to look the same? It's always look at the radial part, look at the tangential part. Of course, don't forget what they mean, because every question's a little bit different. So you got to put together the meaning behind them in order to answer the question. And I think this last one illustrates that really well. This one's going to take some thought. You will see it's nothing beyond anything we've done, but it is something we haven't done before. Maybe it's worth repeating it again, especially since Don, the guy who does the workshop class, and I were just talking this morning about another physics class. It wasn't about you guys. We were thinking, yeah, they just didn't quite kind of catch the big picture. The big picture is know the fundamentals, right? It's at the top of the syllabus. Physics is about knowing how to apply a few fundamental concepts, but powerful concepts, to explain a universal phenomenon. And so we know how to deal with the circular motion, and so we can do all kinds of different problems involving circular motion and involving gravity. And the other class, it was like they had a problem on their test. They just, it seemed like a lot of them were just lost. They wanted to put a formula that we had derived in class or in the book. Well, it wasn't there. We didn't do it. That wasn't the point of the problem. The point of the problem was, could you put together the thought process to come up with that formula? And I do think this one does that really well here, 54. 54 is going to say, okay, remember all this stuff you learned about gravity? And remember this stuff we're learning now about circular motion? Can you put those two together and answer this question? It reads like this. It's too bad it's broken up on 2 pages. Let me go to the next page here and show you at least the picture first. So here's somebody standing on this hemisphere-shaped rock. They're right at the very top, and they kick a soccer ball. All right? Now keep that in mind as I go back up here and read the problem. It says, a person standing on top of a hemispheric rock of radius capital R kicks a ball, which is initially at rest at the top of the rock, to give it a velocity, v sub I, as shown. Okay, now notice, it's a horizontal kick. So it's not angled up or shot down, which I guess if you're at the top, you can't really shoot it down. It's, tangentially flat at that point. But you could have kicked it up. But doesn't. It kicks it straight out. Horizontal shown. A, What must be the minimum initial speed if the ball is to never hit the rock after it is kicked? So we want it to go out. Now, of course, you know gravity is going to make it drop, right? But we want to kick it hard enough that it doesn't hit the rock. Now, obviously, if you kick it really hard, it'll never hit the rock. But the question is, what is the minimal speed? It will never hit the rock. Then it goes on in B, with this initial speed, how far from the base of the rock does it hit the ground? And so I think it'll serve us better to have the diagram up here. So I'll scroll down to the next page. Here it is. Here's the hemisphere, radius r. It lands some distance x. How far? That's the part B. All right, well, let's talk about all of this. Let's start, first of all, with our hemisphere. Here's the soccer ball up at the top. It's got some radius r. We know if you were to kick it with a small amount of speed, it would want to go in that path. Now it hit the rock and it couldn't go into that path. But if the rock wasn't there, a slow speed would look like that. Fair enough? A little faster speed might look like that. Faster still might just miss the rock. But since the path of a projectile is a parabola, you could not make it go in a circle without hitting the rock. That's not what gravity does, right? So it can't follow the ideal path of a circle and be under the effect of gravity. Now it could roll down the rock and be touching the rock and then go in a circle. And so we know then that what's going to happen is there's going to be kind of a connection at the beginning between the shape of the hemisphere and the shape of the acceleration, the turn. The radial acceleration, there's the key, that's going to give it, so it's going to land right here. Now, obviously, a really hard kick, and even harder still, is clearly going to miss the rock. There's no doubt about that. But the question says the minimum amount. So again, if you don't kick it hard enough, it ends up rubbing on the rock. But if you kick it hard enough so it doesn't rub, it's got to go so fast not to rub at the rock, then it goes beyond. And so there's this little area, x here, or length x, that the ball could not land without hitting the rock. And that's essentially what they're asking here. All right, so let me look at the accelerations here. After the ball has been kicked, but really hasn't moved anywhere quite yet. Because I know when your foot makes contact with it, there's going to be a huge tangential acceleration. That's what makes it go faster. All right, so let me not draw that in my diagram. But after that, then, doesn't gravity pull down on it? So there's gravity. Has an acceleration of g, 9.8. Right? And so at the instant you kick it, it's traveling that direction, so there's velocity. And it then is turning. Isn't this the radial acceleration at that point? So I would say that the radial acceleration is g. And that has to equal v squared over r. Let's talk for a moment here. What if the speed was slow? Well, maybe I'll put it this way. R equals v squared over g. When you first kick it, and you have a low speed, doesn't that mean it has a small radius of curvature? Isn't that why it hits the rock? Isn't it if this radius that you kick it is less than the radius of the rock, isn't it going to hit the rock? So there's the key. What I want then is R to be greater than or equal to capital R, right? I want the radius of curvature that that ball is initially going to have. And so maybe in a different color I should have drawn it here. That when this ball gets kicked, its motion looks something like that. The beginning part right there has a radius of curvature to it. That radius of curvature is given by this equation. So a small speed would mean a small radius of curvature, and if it is less than the rock, it hits the rock. But a really high speed would give it a radius of curvature greater than the rock, and so it would curve with a radius greater than the rock, so it doesn't hit the rock, and it doesn't hit it for the rest of the motion. And so it's really those two pieces that I'm trying to put together. The projectile, the original starting velocity, then is connected to its original radius. Now don't get me wrong, the ball when it's kicked does not go in a circle. In fact, maybe you can see that later on when the ball gets, say, right here. The acceleration due to gravity is still g down. But the center of the circle is here, so only a component of gravity is towards the center of the circle. So that means the radial acceleration is less, and that means the radius of curvature is more. So a good way to describe a ball flying through the air is at this point, all of gravity is in the radial direction. Over here, only a component is, and so the radius of curvature here is bigger than the radius of curvature here. So when you draw a parabola, I think you see that. Where does the parabola have the tightest part of its curve? Right there. And then as you move over here, it opens up and has a bigger and bigger radius of curvature. And that's really what this problem is saying. So you can see why it's a magenta one. You can see why I did it last. It is going to require you to think through, what did we learn about circular motion? What did we learn about projectile motion? Put the two together and you come up with this statement here. So once you do that, you can then substitute these two together and say v squared over g must be greater than or equal to r. Or v squared must be greater than or equal to rg, or v must be greater than or equal to r times g. And so if you kick it with this speed or greater, it won't hit the rock. Lower speed than that, it will hit the rock. I think another thing that makes this problem harder, in any of them, is they don't give you any concrete numbers to work with. They did not give me the radius. Now g I know is 9.8, but they just gave it in terms of radius r. And anytime you have equations that have variables in it, I think for students that's harder for them. They don't see it as clearly as if you put in a number here. And so I can't give you a number here because they didn't give me a number there, but I can give you the formula for what it must be. And I think that was A, right? What's the speed? The other part then is, where does it land? All right, well, let's come back to our rock picture here. Maybe I'll redraw the rock picture here and say there's where it lands. Let me go ahead and call the horizontal distance x. Let's launch it from here, and so this going down would be r. And so let's go back to our projectile motion that we did all those examples on Monday here. Okay. Maybe I should point out though, my x is different than their x. Their x is how far beyond the rock does it land, so we'll come back to that one. But if I pick the origin as being the launch point, and I write out these equations, I would say x equals to the initial position, which is 0, times the initial velocity in the x direction times time, plus 0 acceleration in the x direction. And so that's our fundamental equation for projectile motion that we've been using a lot. 0 here because that's the origin, 0 here because there's no acceleration. In this case, the horizontal speed is this. So I will put the square root of rg and multiply it by t. That's how far this ball is going to go. It depends, of course, on how fast you kicked it and how much time it spends in the air. But again, let me remind you, the same thing you did in the lab on Monday, and I was telling you in class on Monday, use the vertical motion as your clock. And so if we write out the equation for vertical motion, it will get us the time, and we can finish this equation. So I'm going to come over here and write the equation for the vertical motion. Again, putting the origin as the starting point, I would say 0 plus 0. That's the initial speed in the y direction. Remember, we kicked it horizontally. And then I would have a negative 1/2 gt squared, where the acceleration is a negative 9.8. I'm just going to use the symbol g since I've used it here, and there's no point in putting any numbers in here because we can't calculate a number.
Positive then, since g is still g, it's not negative 9.8?
No, g is 9.8 meters per second squared. G does not have a negative with it. So yeah, be careful with that. So I need to put a negative here because the g does not have the negative in it. The g just represents the positive part of it.
You put it in the x area already, the x equals square root of rg. Would that be negative rg or no?
No, because again, back here, I wanted you to know the magnitude of the radial acceleration. And that's why I used the g without a negative sign. Yeah, good point. And that's why we tend to use g. I mean, you could ask, isn't g always down, so why not include the negative in the symbol? But it's really helpful not to. And there's a reason why. A lot of times we want to know just magnitude. So we can put direction by it on its outside and then put its magnitude. Okay. Let me continue because I know in the y direction, then it's going to land at a position down of r. And if it's down, what needs to go in front of it? Negative. Some of you overlooked that for a long time in the lab. I hope that was a reminder to you. Never make that mistake again. And you did that projectile motion. And the whole reason we set it up so you fire the cannonball and it lands on the ground is because you guys measure the ground and you get like 1.1 meters or something. It's so easy to put 1.1 into your equation, but shouldn't it be negative 1.1 if it was down? And so again, you have to be reading each symbol and each meaning of those as you go along here. And so the radius is r, but it goes down, which matches perfectly with the negative that is there. And of course, like any negative sign, I guess if we made the mistake here and made the mistake there, we would still be okay. But hopefully you won't make either of those. So technically there's two negatives on each side, which then we can cancel off. And so now, when I put this over to here, I get 2r over g, take the square root of that. That's the time it would take. And so that's what I was saying, both in lab and last Monday, and now use the vertical motion as your clock. So now that we have time, we can put it into this equation. So I'm going to come back over here. I got the square root of rg, and then I'm going to multiply by the time, which is the square root of 2r over g. And if I put my square root stuff all together, then the g upstairs will cancel with the g downstairs, and I will have a 2r squared, which comes out to be root 2r. And if you remember your decimal equivalent of root 2, it's 1.41. And so that distance it lands is greater than r, as the picture was showing. So to finish the question, which says how much beyond the rock, I'll call it delta x. Again, in your author's symbol here, he just calls it x. But I'm going to call it delta x. I would say it lands at root 2r, and I'll subtract off the base of the rock. And if I can, I'm going to go ahead and erase that. And so what I would get is root 2 minus 1 times r, which in its decimal equivalent is 41% of r. And so that's how much further beyond the rock it would have to land. Piece of cake, right? Ready for the test tomorrow. All right. Maybe not quite yet here. But those are the problems. And as I have said in the past, I'll say it again, start working on these problems in chapter 4. Because like I said, they put together chapters 1, 2, and 3, and 4. And so this is your real test here. If you can do chapter 4, you probably can do any problem on the test that would involve like chapter 3 or chapter 2 or chapter 1. Okay? And so that's why I think they make good examples. Well, in the half hour we have left, let's roll into chapter 5. And as I was saying at the beginning of the class, chapter 5 takes us to our next step. That's why we're going to have a test, and then we're going to be working with chapter 5. And I don't want to do too much into chapter 5 quite yet today. I'll wait until next, well, I was going to say Monday, but Monday's a holiday again. I'll wait until next Wednesday. But I know that you're going to be working hard and thinking about chapter 4 and, of course, about the test here. But I do want to bring back your memories of what did you learn in your previous physics class that explained the motion. You no doubt learned about what we call Newton's 3 laws of motion. And so the beginning of this chapter 5, as you'll see when you do the reading, and hopefully you will get a chance to do the reading before I see you again next Wednesday. And then that means hopefully you did the homework and you did the reading. He runs through Newton's 3 laws of motion. So let me take you back to your previous physics class and say, all right, let's look and remind us of Newton's 3 laws of motion. And let me be clear on the beginning part of this, which if you didn't get this from your Physics 102, let me say it now. These 3 laws explain all motion. That's the key. And so as we start to do our problems here in chapter 5 and in chapter 6, hopefully you will go, oh, all I have to do is apply the first law, the second law, and the third law. It doesn't matter if this is a car that is moving or a plane, an asteroid, a molecule, they all are going to follow Newton's 3 laws of motion. So, what does the first law say? Law number 1. Maybe some of you remember its title. We refer to it as the law of inertia. It doesn't have any math with it, so we will need it. It'll be part of our logic, but it won't really be part of our calculations. And it simply says, an object at rest will remain at rest, and an object in motion will continue in motion with a constant velocity unless it experiences a net external force. Well, let me pause there and kind of just jog your memory back to this one. Like I said, there's no real equations here. It's the second law that's going to have all the equations that we're going to use to do our calculation. But you can now see why it's called the law of inertia. Maybe I should start with that big fancy word, inertia. What does inertia mean? Yeah, resistance to change, right? So probably this morning when the alarm clock went off for you to get up, you probably had a lot of inertia. I'm at rest, I'm lying in bed, please don't make that change, right? Probably the same thing happened. The whole reason you were so tired this morning is because you probably stayed up a little later than you should have. Probably again because, hey, it's late, I'm having a good time, I just love doing my physics problems and I don't want to go to bed. And so you didn't go to bed on time or at a reasonable hour because, again, you were up and you wanted to stay up. You were watching that movie, you were doing that homework problem, you were chatting with your friends, you were exercising, I don't know what you were doing. But it's difficult to make the change. That's what this one is trying to say. From a physics point of view, it resists any change. And so you'll notice that. It says if they're at rest, they want to stay there. Now, do they have to stay at rest? No, things can move. And if you follow it down, it says unless it experiences a net force. So in other words, its natural state would be to say if it's rest, it wants to stay that way. But did you also notice that what if it is not at rest? What if it's actually already moving? What is it going to do then? It's saying the same thing. It wants to continue moving. It doesn't want to come to a stop, and it doesn't want to go faster, and it doesn't want to turn. It wants to continue with the same velocity. And so for things to either go from rest to moving, or if they're already moving, for them to stop or to speed up or to turn, all of those involve changes. And those can only occur if there is what? What we're going to call a net external force here. And so maybe the easiest way to kind of illustrate the law of inertia is with a couple of different experiments, this being one of them. And those of you who had 102 here probably saw all of these. So I'll go quickly. But aren't all these table pieces at rest? And so they want to stay at rest. Now, doesn't mean they have to stay at rest. They could move. But in order to get it to move, what did I do? I had to give it a force. So that's going to be our logic. We're going to look at things. And if we see something at rest and it remains at rest, we know there is no net external force. But on the other hand, if we see that fork flying through the room, what do we know? Well, it was at rest. It's now moving. It must have had a net external force on it. So it's going to help us with our logic. We know what we can have or should have in order for that to happen. This one's kind of fun to do because underneath all of these dishes is paper. And it happens to be fairly smooth paper because as it is smooth, my question is, could I pull it out from underneath all these dishes? And according to the law of inertia, it says these things want to remain at rest. And so I've grabbed some nice smooth paper so that there'll be very little to no friction. And if there's no friction, which we'll say no forces, won't they stay there? So let me give it a try. I think I can pull it out. You guys might want to want it yourself. I don't want to send anyone to the hospital again. But on the count of 3, I'll pull it out. 1, 2, 3. It moved a little bit. But for the most part, it, it was stationary. The same silly game can be played here. Here I have a heavy weight. It's tied with a string on the top and the string on the bottom. Of course, we set it up before class, but these are the same string from the same spool, I guess is what I mean. They have the same strength, if you will. If I were to grab this string and pull downward on it, it would eventually break where? Would the string break below the weight or above the weight? Who thinks when I pull on it, it's going to break up here? Okay, just a couple of you. Who thinks when I pull on it, it's going to break down here? Okay, so most of you think this one's going to break. So I will pull on it. I probably should have taken a bunch of bets, $1 each, because which one broke? Top one. So I guess I would have won more money than I had to pay out. But on the other hand, if I take the identical situation and I pull on it, the bottom one breaks. Why? Did you notice the difference in the way I pulled it? And of course, notice the different string that broke? This is how I make money on the weekend, taking bets on State Street. Yeah. And so depending on how the bets go, I can control which string breaks, but I'm really taking advantage of what I would call the law of inertia. In other words, this object's at rest and it what? Wants to remain at rest. Now it will start to move. It will move if there's an external force, and I would say I am beginning to put an external force, but the quick jerk is such a fast force that I really haven't given time for this thing to respond. And by not giving it time to respond, it really has not pulled on the upper string, and it really hasn't supplied any tension to this upper one. Whereas the first time when I broke it, this one, I took the string and I pulled it harder and harder and harder and harder and harder, but I did it at a gentle rate. So eventually that one would break, because that gave this one a chance to move. And I would go far to say that this one would break because both this weight and my hand are tugging on it. Whereas the bottom one, I would say just my hand is tugging on it. And so I'm taking advantage of what you would call the law of inertia. Maybe you've noticed the law of inertia in your everyday life. I mean, a good example of exactly pulling these is often what I do when I'm making something in the microwave. I'll often throw my burrito in there, put it in there for a couple seconds or minutes, grab the burrito with one hand, reach across the kitchen where the paper towels are. How do you take a paper towel off a roll with one hand?
Pull really quick.
Yeah, it's a quick jerk. Actually, it's two parts. Don't at first you pull slowly so that it unrolls. See, the paper towels have inertia. And if you want it to respond, if you want it to move, you don't pull it quickly. You got to give it a chance to respond. That's the inertia. It's at rest and wants to stay at rest. So at first you pull kind of slowly. Then when you get that paper towel to the edge, then you pull quickly, and then that pulls the paper towel away from the whole roll, and it tears. And you are taking advantage of the law of inertia to do that. In fact, maybe you've even noticed those rare occasions where you're at the end of the roll. What happens when there's only like 5 little sheets left and you do a quick pull? Any different? Yeah, doesn't the whole thing come unwinding? And so in other words, it doesn't, at that point, it doesn't have much inertia. It doesn't have a lot of material left. The spool or the roll is mostly empty. And so it can respond. It has very little inertia. I noticed this, unfortunately, the other day. I was walking in, and my door kind of goes like this and makes kind of a sharp turn into kind of a narrow little walkway into this kitchen. And there's not much space, and the counter's right there. And I'm always hitting my hand on the edge of the counter. Now, when I'm not carrying any groceries in, I can walk by and I'll hit it. Oh, bummer. and my hand just kind of hits the side, bounces off, and oh yeah, my hand hit. But what happens if I'm holding a bag of groceries that is loaded, say, with canned goods and is pretty heavy, got a lot of inertia? What's going to happen now? Right, it's got inertia. It's a lot harder to change its motion. And so what ends up happening is the counter's got to push a lot harder on my hand to change the direction of not just my hand, but it's the hand and all those groceries. So it pushes harder, and it hurts a lot more. And so when I hit it there, it's like, ow, that did it. And so that is a good example of that law of inertia, that huge difference between what is going on when you have material, a lot of it, versus a little bit of it. Well, let me kind of show you over here with this one. Here is the one that, what if it's already in motion? Won't it keep going? Wait, let me try again. And so if it's already in motion, doesn't it keep going in motion? This one doesn't seem to keep going in motion. Yeah, did we break the laws of physics? No, and you guys see it right away. You should anyways, right? I think you saw this already in your Physics 102. What's going on here? There is an external force. There's friction, there's rubbing going on here. It's one of the reasons Newton had a hard time convincing people of this law, because every time they kept pushing things and sliding, they said, no, look, it comes to a stop. But no, there is an external force. It's friction. If you had something without any friction, once it's in motion, it will stay in motion. And so if you had something way out in outer space, like this giant asteroid, it's heading towards the Earth. Hopefully not, but and it's traveling at 25,000 miles an hour straight for the Earth, and it's way out past Pluto somewhere. Why does it keep moving? What keeps pushing it? The little Martians driving the spaceship right towards Earth? No. Inertia. It doesn't need anything to keep it going. Once it's already going, it will keep going. And I think you can see that best with these wheels. These wheels, for those of you who are close enough, you can hear them and see them. They roll really well. They're what we call a low friction bearing, and they roll for a long time. And so if I put them here and I give it a little push, it just keeps going. Doesn't stop. Oops. Until there's a force on it. And so it will just keep going. And so there's the first law. Well, in the time we have left, let's try to get all three of them out here. How about the second law? This one is the mathematical one. I'll put it in math terms. I'll say it in verbal form. I would even say this second one is a continuation of the first one, because doesn't this first one really tell me whether there is or is not an acceleration, right? And so if there are no forces, the object should either remain at rest or it should remain going in a straight line with the same speed. On the other hand, this one does say if there is a net force, then this does say it will change its speed. Maybe it will go faster, maybe it will go slower, maybe it will turn to the left, maybe it will turn to the right. If it was at rest, maybe it will start to move. But this one is saying you will get an acceleration. And so the second one is giving you a little formula for calculating how much acceleration will you get. And so this is the one that I will often joke with you, and I guess I'll start now. Even though you're working on Chapter 4, you're going to get to Chapter 5. Would you like the answer to all the homework in Chapter 5? There it is. You're looking at it. How hard could it possibly be? I will show you and tell you. Start right there. fill in the details. 2 hours later, you'll be done with the first problem. You have about 30 problems to do. And so after 60 hours, you'll finish chapter 5 homework. All right. And hopefully I'm joking. Hopefully it won't take you quite that long. But I am trying to come across very seriously that this is the fundamental idea. This will tell you whether there is or is not an acceleration. This will allow us to calculate what is the value of that acceleration. And once we know the value of that acceleration, can't we use all the stuff that we just learned in chapters 1 through 4? And that's the little game we're going to play here in chapters 5 and chapter 6, believe it or not. We won't learn a single new thing in chapter 6. How easy is the next 2 weeks going to be? That's it, for 2 weeks. All right. But as you see, we'll put them in the problems, and it'll be a lot of deductive reasoning. And so we'll be able to handle some pretty hard problems. Let's talk about this. This is saying, and I think this is how you learned it in your Physics 102 class, it says that yes, well, let me go back here. This will say, yes, you have an acceleration. So this will say, well, how much acceleration do I have? Well, this is saying it depends on 2 factors. The first one is how much force, how much are you pushing on the objects. But the other one is saying how much inertia or how much mass do you have? How much are you resisting it? So more of this means you get more acceleration. But more of this means you get less acceleration. Now, you can see it here, I think, really well with our cart. If I take this one and I have this little plunger and I push the plunger barely in, that means I'm going to get a small amount of force. And if I release that small amount of force, I get a small amount of acceleration. But what if I put the plunger all the way in? You can imagine now I'm going to get a lot more force. And therefore, a lot more acceleration. So again, not a big surprise. Now, even if you hadn't even had physics before this, I think you can relate that, hey, more force, more acceleration. You do that when you go to run, ride a bike, drive a car. Those are pretty obvious. You want more acceleration, you give more force. But that's not the whole story. What's the other part of this story? Is the mass. Notice again that if I push the plunger all the way in and I put it against here and I release it, that's a pretty good acceleration. But what if I push the plunger all the way in? So it's still the same force, but I put more mass on here. What happens there? Lower acceleration. So it takes both factors to contribute to what is the final amount of acceleration. How much net force do I have and how much mass do I have? Now, we're going to take this one step further than you did in your Physics 102. Aren't these vectors? And so I'm going to add to this equation by putting an arrowhead over it. And what I mean by that then is, wouldn't we have an acceleration in the x direction and an acceleration in the y direction? Wouldn't the acceleration in the x direction be the net force in the x direction divided by the mass? And the acceleration in the y direction, the net force in the y direction divided by the mass? Of course, we could just ask what is the magnitude of the total acceleration. Well, that would be the magnitude of the total net force divided by the mass. And so we can look at this equation in a more complex way than we did in the last physics course we had. We can look at the acceleration in terms of its components, or we can look at the acceleration in terms of its magnitude. But we have to do vectors. And notice we're adding them together. What is really meant by net force anyways? Yeah, again, going back to your 102, you probably learned this, but the reason we say net force is when you have an object, you may have more than just one force on it. So to figure out its motion, you have to combine all the forces, right? You have to add them together. That's what we mean by net force. Your net force. How does your car move? How does the baseball move? How does the molecule move? How does the asteroid move? If I have this asteroid and I want to know its motion, I need to look at not just the force of, say, the sun pulling on the asteroid, but how is Jupiter pulling on the asteroid? How is the Earth pulling on that asteroid? How is the moon pulling on that asteroid? And when I put all those together, that's the net force. That would determine the motion of it. And that's what a NASA scientist would have to do to figure out, is this asteroid going to hit Earth or not? Well, we need to see its motion. And its motion is influenced by a lot of forces. And in that case, its forces vary depending on how close they are to Jupiter or how close they are to Earth. But this is really force 1, then added to force 2, then added to force 3, and so forth and so on, depending on how many forces you have. And that's what's going to make the homework problems long and hard. It's not the ideas. The idea is pretty simple. There it is. There's the answer to all the homework problems right there. Add up all the forces. But when you sit down to do a problem, you're going to realize, wow, there's a lot of forces here. I've got this box here, and somebody's pulling it to the left, and someone's pulling it to the right, and gravity's pulling it down, and the table's pushing it up, and then it's rubbing on the ground, and there's a friction, and then it's rubbing against the wall, and it's rubbing against another box, and there's some more friction. Oh my gosh. Yeah, keep track of all those, and get the net force. Once you figure out the net force, then it's equivalent to just one force, and it's a pretty easy problem. We're going to write it this way. The sum of the individual forces. And so again, hopefully I'm emphasizing, we're not doing any new physics that you didn't already see in 102. We are putting more math into it. So maybe for the grand finale here, this then is Newton's second law. Take the forces involved and add them up. And of course, one of the challenges you're going to find here is make sure you recognize whether there is or is not a force. Because if there's like 4 forces on this box and you only see 3 of them, then you start adding them up, you're stuck. You're going to get it wrong because you did not see that 4th force. And then so one of the things why we'll keep talking about in this chapter is, how many forces do you see on this box? Do you see 4? Do you see 5? And so we'll talk about them to make sure you get some practice recognizing all the forces. Then you can add them all together. Then you can divide it by the mass, and then you will find the acceleration. And then you'll have the acceleration, then you can figure out its velocity, and then from its velocity you can get its position. Okay, now I understand why the problem's so long. Do you see all that? In a diagram form, I guess I would put it this way. You are going to add up all the forces. That is going to give you the net force. From the net force, you are going to get the acceleration. From the acceleration, you are then going to get the velocity, and from the velocity, you are going to get the position. I will circle this and say, here is our first test. This is chapters 1 through 4. This is why we've just spent these first 4 weeks dealing with. This is what you will still dealing with. But once we move on past chapter 4, we are going to be doing a lot of that. This is chapters 5 and chapters 6. Looking at forces. What forces are involved? How many are they? Add them together. Treat them like vectors. Add them together with our I hats and our J hats. Do our two-dimensional motion. Once we get the two-dimensional acceleration, we can get the two-dimensional velocity and the two-dimensional position. Right? And that's why it's going to take 6 weeks to go through this little diagram and make sure we really get the whole idea of chapters 1 through 6 before we move on to some other ones. Well, as you know, in the 5 minutes we have left, there is the third law, right? Newton's 3 laws of motion. And so what does the third law say? Yeah, the third law, and maybe I should even point this out, the third law is not a continuation of the first and the second. So the first and the second to me are kind of one and the same. This tells me whether there is or is not an acceleration. And then this tells me how I can calculate that acceleration. But the third law is what we call the action-reaction one. And being low on time, I might just draw a quick picture and not spell out the words. But if I have object 1 and another object over here, object 2, I won't even say what they are, just 2 objects. I don't know, maybe it'd be easier if you thought of them as maybe the Earth and the moon. But if this is the Earth and this is the moon, the Earth pulls on the moon. I'll call it force. So if the Earth pulls on the moon, what else happens? Yeah, the moon pulls on the Earth. And how much? Yeah, they're equal. And so we'll label it this way, that this will be the force from number 1 on number 2. And it'll be a vector, it has a direction. And this over here, we'll say this is the force from number 2 and on number 1. And so kind of keeping track of our prepositions is important. What is the force from and what is it on? And the math here simply says force 1, 2 is equal but opposite of force 2, 1. And that's our labeling of our forces, equal and opposite. Well, let's see if I can illustrate them in a little time we have left here. If I put these together and I release the plunger, you will notice they move out. How does the force on this one compare to the force on that one? They're the same. What if, on the other hand, I load this one with a lot more mass and release the plunger? How does the force on this one compare to the force on that one? They're still equal. Does that mean the accelerations are the same? No, but the forces are. So the third law is actually a pretty easy one that students often get confused with the second one, because what is different is the acceleration, not the force. It doesn't matter how big the object is. It doesn't matter how fast they are moving. If 1 puts an object on 2, then 2 puts a force on 1. They are same. They are equal. A quick demonstration, we'll call it a go. Watch this one. How does a rocket ship work? Well, if this is the fuel in my rocket ship, then if the engine puts a force on the fuel that way, then what else happens? There's a force equal and opposite. And so the fuel will go one way, but the rocket ship will go the other way. How does an airplane or a boat work? It's got a prop. Puts a force on the air that way. So what happens to the boat or the airplane? It goes that way. How do the forces compare? The same. And one fun one just to finish off. Here I have a bunch of carbon dioxide. It's compressed in here. If I open the valve, it will go shooting out that way. It'll put a force on the carbon dioxide that way. But what does the third law say? There will be an equal amount of force. Not more, not less, that way. Now that's not to say this will go that way with the same acceleration, because the air is going to have a lot less mass and have a really large acceleration. And because of that, I won't point it towards you guys. I will point it that way. And of course now it will blow these papers off the door and all kinds of things over there. But it can be quite a bit of force. And I like it because I can write it. And so I can blast the air that way. And I go that way. All right, well, good closure. Work on these. I'll see you in a week.